Hello, in this lecture we'll answer two questions. In the first question, we'll find out the area of this circle that is inside square ABCD. And in the second question, we'll find out the value of the area of the green shape that is inside the quarter circle. We'll start with the first question. In the drawing, we have square ABCD. Inside square ABCD, we have a circle. The angle CBT, this angle equals to 30 degrees. Line segment PD equals to 5 units. And our mission is to find out the area of this circle. So first of all, we'll define the center of this circle as O. We will join points O and P together by a straight line. Point O is the center of the circle. Point P is the point on the circle itself. Therefore, OP is the radius of this circle that we define as R. And we have the radius OP that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees and this angle will be equal to 90 degrees. Likewise, we join points O and Q together by a straight line. Again, point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle that is equal to R. And we have the radius OQ that is drawn to the point of tendency, therefore this angle will be equal to 90 degrees according to rule number 1. And we know that all the angles inside square ABCD are right angles, so this angle equals to 90 degrees. This angle will be also equal to 90 degrees. This angle equals to 90 degrees. And finally, this angle will be equal to 90 degrees. So actually, inside quadrilateral AQPO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So 270 degrees plus 90 degrees equals to 360 degrees. That is the sum of the angles in any quadrilateral. So this angle must be equal to 90 degrees in order to complete the sum of the angles in this quadrilateral to 360 degrees. This angle must be equal to 90 degrees. So inside quadrilateral AQPO, we have 4 right angles. Therefore, quadrilateral AQPO is a rectangle. So I write it down. Quadrilateral AQPO is a rectangle. Why? Because it has 4 right angles. And we also note that the opposite sides of a rectangle are equal to each other. That is to say, side AQ equals to side PO. AQ equals to PO, but we have already found out that PO equals to R. So I can write here that PO equals to R. And for this equation, AQ equals to PO equals to R, we will derive that AQ is also equals to R. Here we can write in the drawing that AQ equals to R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that AP equals to QO. AP equals to QO, but we have already found out that QO equals to R. And for this equation, AP equals to QO equals to R, we will derive that AP is also equals to R. AP equals to R. Therefore, quadrangle AQPO is not a rectangle but a square because of the fact that all of its sides are equal to each other. They are equal to R, the radius of this circle. Okay, in addition, we also know that all the sides of square ABCD are equal to each other, of course. That is to say, side AD equals to side AB in square ABCD. AD equals to AB. Okay. In square ABCD, we know that side AD equals to side AB. Okay. What is the length of side AD? Side AD equals to R plus 5. And it must be equal to side AB. Side AB equals to R plus QB. So, in conclusion, we found out that R plus 5 equals to R plus QB. We subtract R from this equation and we get that 5 equals to QB. QB equals to 5 units. In the next step, I will present to you rule number 2 and we will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So we have the common external point P. From the common external point P, we have tangent PA to the circle and tangent PB. And according to this rule number 2, PA equals to PB. We can implement rule number 2 in our drawing. Why? Because in our drawing, if we focus on the common external point B, from the common external point B, we have two tangents to this circle, tangent BQ and tangent BS. And according to rule number 2, BQ equals to BS. But we have already found out that BQ equals to 5 units. BQ equals to 5 units. And from this equation, 5 equals to BQ equals to BS, we will derive that BS is also equals to 5 units. Here, BS equals to 5 units. In the next step, we will join points Q and S together by a straight line. By joining points Q and S, we created here triangle BQS. What is the side of angle QBS? Although it is very easy to see that the side of this angle, angle QBS, equals to angle ABC, the right angle ABC, minus angle TBC. Again, angle ABC minus angle TBC equals to angle QBS. So angle ABC equals to 90 degrees, minus angle TBC equals to 30 degrees. 90 degrees minus 30 degrees, it is 60 degrees. So angle QBS equals to 60 degrees. So we'll focus on triangle QBS. In triangle QBS, this angle equals to 60 degrees. Therefore, the sum of those two angles must be equal to 180 degrees minus 60 degrees, that is 120 degrees. So the sum of those two angles must be equal to 120 degrees. So in the right triangle, in triangle QBS, this triangle QBS, those two sides, they are both equal to 5 units, therefore they are equal to each other, and we have the rule that in front of equal sides in the triangle, there are equal angles. So those two angles that are located in front of equal sides must be equal to each other. So if this angle is alpha, then this angle must be also equal to alpha, and as I already mentioned before, 1 minute, that the sum of those two angles must be equal to 180 degrees minus 60 degrees, that is 120 degrees. That is to say, alpha plus alpha equals to 120 degrees. So alpha plus alpha equals to 120 degrees. Alpha plus alpha is 2 alpha, that is equal to 120 degrees. We divide this equation by 2, and we get that angle alpha equals to 120 degrees over 2 is 60 degrees. So I found out that angle alpha equals to 60 degrees. And this angle alpha equals to 60 degrees. This is angle alpha, that is equal to 60 degrees. So actually, inside triangle QBS, all of its angles are equal to 60 degrees. Therefore, triangle QBS is an equilateral triangle. Triangle QBS is an equilateral triangle. And we know that in equilateral triangle, all the sides are equal to each other. That is to say, side QB equal to side SB. Both sides are equal to 5 units, and it is equal to side QS. Therefore, side QS must be also equal to 5 units. You found out that QS equals to 5 units according to the rule that all the sides of an equilateral triangle are equal to each other. In the next step, we will join points O and S together by a straight line. Point O is the center of the circle, point S is the point of the circle itself. Therefore, OS is the radius of this circle that is equal to R. We have the radius OS that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. So, in the next step, I will copy quadrilateral OSBQ in a new page and we'll analyze quadrilateral OSBQ. Okay. Angle OSB equals to 90 degrees according to rule number 1. So actually this is quadrilateral QBOS that I copied from the original drawing. In quadrilateral QBOS, angle QOS is the missing angle. What is the size of the missing angle? Angle QOS. The size of the missing angle, angle QOS. The size of this angle will be equal to 360 degrees. That is the sum of the angles in any quadrilateral minus the sum of the three known angles, minus 90 degrees plus 90 degrees plus 60 degrees. So the size of the missing angle, angle QOS, will be equal to 360 degrees minus 90 degrees plus 90 degrees is 180 degrees. 180 degrees plus 60 degrees is 240 degrees. So therefore the missing angle equals to 360 degrees minus 240 degrees, it is 120 degrees. So this angle equals to 120 degrees. The missing angle QOS, the size of the missing angle equals to 120 degrees. Here, this angle QOS equals to 120 degrees. In the next step, I will present to you the law of cosines, and we will implement the law of cosines in the green triangle, triangle QOS. Okay. So what is the law of cosines? The law of cosines is true in any triangle So if we have triangle ABC that could be any triangle, this is triangle ABC. And we know that the length of side AB is A units, the length of side AC is B units, the length of side BC is C units, and the angle between side AB and side AC is theta. Then, according to the law of cosines, we get here that c squared equals to a squared plus b squared minus 2 times a times b times cosine theta. I repeat again, in the right triangle ABC that could be any triangle, c squared equals to a squared plus b squared minus 2 times a times b times cosine theta. Actually, we can implement the law of cosines in the green triangle QOS. So I'll copy the green triangle QOS in a new page and we implement the law of cosines in triangle QOS. So this is my triangle QOS that I copied from the original drawing. Side QS equals to 5 units, OS equals to R, OQ equals to R, and angle QOS, this angle equals to 120 degrees. According to the law of cosines, we get here that 5 squared equals to r squared plus r squared minus 2 times r times cosine 120 degrees. Okay, so 5 squared, again 5 squared equals to r squared plus r squared minus 2 times r times cosine 120 degrees. 5 squared is 25. That is equal to r squared plus r squared is 2r squared. Minus 2 times r is minus 2r squared. And cosine 120 degrees equals to minus 1/2. So here we have 2 in the numerator and 2 in the denominator. So 2 will get cancelled. Minus times minus is plus. So in total, this expression will be equal to plus r squared. So we get here that 25 equals to 2r squared plus r squared is 3r squared. So 25 equals to 3r squared. We divide this equation by 3 and we get that r squared equals to 25 over 3. And we know that the area of our circle is equal to pi r squared. But we have already found out that r squared equals to 25 over 3, so we substitute r squared by 25 over 3, and we get that the area of our circle equals to pi times r squared, and r squared is 25 over 3. So in conclusion, we found out that the area of our circle equals to either 25 pi over 3 square units, or in terms of numbers, it is equal to 26.18 square units. It again, the area of our circle equals to either 25 pi over 3 square units, or in terms of numbers, it is equal to 26.18 square units. We finished with the first question. In the next step, I will present to you the second question, and we will solve the second question in 3 different methods. In the drawing, we have a quarter circle. This is a quarter circle. Inside the quarter circle, we have a small circle, We know that line segment CD equals to 8 units, angle ACD equals to 90 degrees, and our mission is to find out the value of the green area. We start with the first method, and we define the center of the small circle as J. We will define the point of tendency of tangent CD with the small circle as E. We will define the point of tendency of tangent OB with the small circle as F. We will join points J and E together by a straight line. Point J is the center of the small circle. Point E is the point of the small circle itself. Therefore, JE is the radius of the small circle that we will define as R. We have the radius JE that is drawn to the point of tendency. Therefore, this angle will be equal to 90 degrees according to rule number 1. Likewise, we will join points J and F together by a straight line. Again, point J is the center of the small circle. Point F is the point of the small circle itself. Therefore, JF, it is also the radius of the small circle that is equal to R. And we have the radius JF that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees. Because of the fact that A or B, this shape is a quarter circle, it means that point O is the center of the quarter circle. Angle A or B, this angle must be equal to 90 degrees. And also AO must be the radius of the quarter circle that we define as capital R. Okay? So AO is the radius of the quarter circle. It must be a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees according to rule number 3, that is the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of AO at point C? We have this angle that is equal to 90 degrees plus the missing angle in total, they must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in order to complete the sum of the angles on this side of the straight line AO at point C to 180 degrees. This angle must be also equal to 90 degrees. Okay. In the next step, from the center of the small circle, that is to say from point J, we will draw perpendicular on CO. Again, from point J, we draw perpendicular on CO. So this angle equals to 90 degrees. And this angle will be equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point J and CO as T. So here inside quadrilateral CETJ, inside the upper small quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Likewise, inside the lower quadrilateral, the small lower quadrilateral TJOF, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So, angle EJF, this angle EJF equals to 90 degrees plus 90 degrees, it is 180 degrees. So, angle EJF equals to 180 degrees, and therefore angle EJF is a straight line. And if angle EJF is a straight line, it means that line segment EJF is a straight line. And if line segment EJF is a straight line, it means that EF, line segment EF is also a straight line. Line segment EF is a straight line. And if line segment EF is a straight line, it means that quadrilateral CEOF, this quadrilateral is a rectangle. I write it down, quadrilateral CEOF is a rectangle. Why? Because it has 4 right angles. Quadrilateral CEOF is a rectangle. First of all, we proved that EF is a straight line. Then, if EF is a straight line, then inside quadrilateral CEOF we have 4 right angles. Therefore, quadrilateral CEOF is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say CO equals to EF. CO equals to EF, but we have already found out that EF equals to R plus R, that is 2R. And from this equation, CO equals to EF equals to 2R, we will derive that CO is also equals to 2R. Here, CO equals to 2R. Okay. In the next step, we join points O and D together by a straight line. Point O is the center of the quarter circle, point D is the point of the quarter circle itself. Therefore, OD is the radius of the quarter circle, that is equal to capital R. In the next step, we will implement the Pythagoras theorem on the right green triangle, triangle COD. Here by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is OD, therefore the square of the hypotenuse is OD squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to CO squared plus CD squared. I'll repeat again. In the right green triangle, triangle COD, according to the Pythagoras theorem, we get that OD squared equals to CO squared plus CD squared. So here, OD equals to capital R, therefore OD squared is capital R squared. That is equal to CO squared. CO equals to 2R, therefore CO squared is 2R squared, that is 4R squared, plus CD squared. CD equals to 8 units according to what is given as the equation, therefore CD squared is 8 squared, that is 64. So in conclusion, found out that according to equation number 1, capital R squared equals to 4R squared plus 64. Here we subtract 4R squared from this equation number 1, and we get that according to equation number 1, capital R squared minus 4R squared equals to 64. Okay. But what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape equals to the area of the quarter circle minus the area of the small circle. I'll repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. Okay? And the area, what is the area of the quarter circle? The area of the quarter circle is equal to pi times capital R square over 4. Repeat again, the area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle. The area of the small circle is pi R square. So here we take pi over 4 as a common factor out of those two expressions. So what is left from capital R square over 4 after we took from it pi over 4 as a common factor? What is left? It is actually capital R square. And what is left from minus pi R square after we took from it pi over 4 as a common factor? What is left is actually minus 4 R square. Why? Because minus 4 R square times pi over 4 equals exactly to minus pi R square. Here we have capital R square minus 4 R square. But we have already found out that capital R square minus 4 R square equals to 64. That is to say, we can substitute capital R square minus 4 R square in this equation by 64. We'll do it now and we'll get that this expression in total equals to pi over 4 times 64. 64 over 4 is 16, so this expression in total equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. Okay, so finished with the first method. In the next step, I present to you how to find out the area of this green shape according to the second method. In the second method, we follow the figures that we have already found out in the first method. We have already found out that CO equals to 2R. We have already found out that this angle equals to 90 degrees. This angle, it is also equals to 90 degrees. We have already found out that AO is the radius of the quarter circle that is equal to capital R. Okay. What is the value of line segment AC? It's very easy to see from the drawing that AC equals to AO minus CO. Again, AO minus CO equals to AC. AC equals to AO minus CO. That is to say, AC equals to AO, that is equal to capital R, it is the radius of the quarter circle, minus CO. CO equals to 2R. So in conclusion, we found out that AC equals to capital R minus 2R. So in the next step, we'll complete the quarter circle to a circle. So I completed the quarter circle to a circle. We will extend the radius AO by a straight line until it touches the circle. We will define the touching point of the extended radius AO in the circle as T. So here point O is the center of the circle, point T is the point of the circle itself, therefore OT is the radius of the big circle that is equal to capital R. We will extend the straight line DC by a straight line until it touches the circle, and we define the touching point of the extended straight line DC in the circle as point M. We join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the big circle that is equal to capital R. So here we extended the straight line DC by a straight line. When you extend the straight line by a straight line, the result DM must be also a straight line. So DM is a straight line. If we focus on the lower side of the straight line DM at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have at the lower side of DM at point C? This angle equals to 90 degrees. Plus this angle, in total, they must be equal to 180 degrees according to rule number 3. So the missing angle must be also equal to 90 degrees in order to complete the sum of the angles in the lower side of MD at point C to 180 degrees. The missing angle must be also equal to 90 degrees. Okay. In the next step, we join points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself. Therefore, OD is the radius of the big circle that is equal to capital R. So we have here two right triangles, triangle MOD, triangle MOC, this right triangle, and triangle OCD. We prove that those two right triangles can go into each other. So we prove that the right triangle, triangle MOC, can go into the right triangle, triangle OCD. So why those two right triangles can go into each other? First of all, CO is a common side that belongs to both triangles, therefore CO equals to itself as a common side that belongs to both triangles. CO equals to CO is a common side that belongs to both triangles. In addition, side MO equals to side OM. They are both the radii of the big circle, therefore they are equal to each other. MO equals to OD equals to capital R. So we actually proved that one perpendicular and the hypotenuse of those two right triangles can go in. Therefore, it is enough to prove that the two right triangles can go into each other. I'll explain you why. Because when we prove that two right triangles can go in the hypotenuse and one perpendicular, then the first side must also can go in. I'll explain what I mean. If we have triangle ABC, this is triangle ABC, Triangle ABC is a right triangle. This is triangle ABC. The hypotenuse AC equals to 5 units and the perpendicular AB equals to 4. And we have another right triangle, triangle DEF, that is also a right triangle. The hypotenuse in this right triangle, it is also DF equals to 5 units also, and the perpendicular DE is perpendicular also equals to 4 units. So those two right triangles have the hypotenuse in both those right triangles are equal to 5 units, and the perpendicular are equal in both those two right triangles. The perpendicular AB equals to 4 units, and here the perpendicular DE equals to 4 units. So those two right triangles can go into each other in their perpendicular and the hypotenuse. Then the third side must also can go in. Why? Because according to the Pythagoras theorem, the third side BC, what is the value of the third side BC? According to the Pythagoras theorem, BC will be equal to the square root of 5 square minus 4 square. 5 square is 25, minus 4 square is 16. 16 minus 25 is 9, and the square root of 9 is 3. So we found out that the third side BC equals to 3 units, and here the third side EF, it is also equals to the square root of 25 square minus 4 square. That is also 3 units. So we actually found out that if we have two right triangles that can go to each other in their hypotenuses and one perpendicular, then the third side must also can go in. That is to say, the third side BC here equals to 3 units, and the third side in this right triangle DEF, it is also equals to 3 units. And we actually proved that those two right triangles, triangle MOC and triangle OCD, perpendicular to each other, can go into each other in their in one perpendicular CO and in their hypotenuses. Therefore, the third side must also can go into those two right triangles, and therefore those two right triangles can go into each other according to side rule. Okay, so I write it down. We found out that triangle MOC can go into triangle OCD according to side rule. Why? Because we know that two sides of those right triangles can go in, and the third side must also can go in according to the Pythagoras theorem. Therefore, those two triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we will derive that side DC equals to side CM. Side DC is equal to side CM according to the rule that corresponding sides in congruent triangles are equal to each other. those two right angles can go into each other, therefore the corresponding sides, that is to say DC and CM, must be also equal to each other. Okay, so CM equals to DC, but we have it is given us the equation that DC equals to 8 units. Here, DC equals to 8 units according to what is given as the equation. And for this equation, 8 equals to DC equals to CM, we will derive that CM is also equals to 8 units. Here, CM equals to 8 units. In the next step, I will present to you rule number 11 and we will implement rule number 11 in our drawing. According to rule number 11, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 11 in our drawing. Because in our drawing, we have chord AT that intersects with chord MD at point C. Again, chord AT intersects with chord MD at point C. So I write it down. Chord AT intersects with chord MD at point C. Point C is the intersection point of chord AT with chord MD. I repeat again. Now, moving, we have chord AT that intersects with chord MD at point C. Therefore, according to rule number 11, we will get that MC times CD equals to AC times CT. Again, MC times CD equals to AC times CT. I write it down. MC times CD equals to AC times CT. I'll repeat again. According to rule number 11, MC times CD equals to AC times CT. Okay. MC equals to 8, CD equals to 8, MC times CD is 8 times 8, that is 64, that is equal to AC. AC equals to capital R minus 2R times CT. What is the value of CT? CT equals to capital R plus 2R. Again, CT equals to capital R plus 2R. So in conclusion, we found out that 64 equals to capital R minus 2R times capital R plus 2R, or 64 equals to capital R plus 2R times capital R minus 2R. So what is the value of the expression capital R plus 2R times capital R minus 2R? According to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. In our specific expression, A equals to capital R and B equals to 2R. Therefore, this expression equals to A squared minus B squared. A is capital R, so A square is capital R square minus B square. B equals to 2R, so minus B square is minus 2R square. So in conclusion, we found out that this expression capital R plus 2R times capital R plus 2R equals to capital R square minus 2R square. That is to say, 64 equals to capital R square minus 2R square is minus 4R square. So in conclusion, we found out that 64 equals to capital R square minus 4R square. Okay, but what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. I repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R square over 4. The area of the small circle is pi R square over 4. Here we took pi over 4 as a current factor out of those two expressions, and inside the brackets we left only with capital R square minus 4R square. But we have already found out that capital R square minus 4R square equals to 64, so we can substitute capital R square minus 4R square by 64. So we'll do it now, and we get that this expression in total will be equal to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. Okay, so we finished with the second method. In the next step I'll present to you how to find out the area of the green shape according to the third method. In the third method, here we have already found out in the first method that CO equals to 2R, that this angle equals to 90 degrees. This angle it is also equal to 90 degrees. We have already found out that OA equals to capital R, it is the radius of the quarter circle. And we have already found out that AC, in the second method, that AC equals to capital R minus 2R. Okay. In the next step, we will complete the quarter circle to a semicircle. we'll extend the radius AO until it touches the semicircle. We'll define the touching point of the extended radius AO in the semicircle as T. So here, point O is the center of the semicircle, point T is the point of the semicircle itself, therefore OT is the radius of the semicircle that is equal to capital R. We extended the radius AO by a straight line. The radius AO is a straight line, and when you extend a straight line by a straight line, the result must be a straight line. So the result of extending the radius AO is AT. Therefore, AT must be also a straight line. So we have here a straight line AT. The straight line AT passes through the center of the semicircle, and so we can view AT, you can see AT as a chord. So we have here chord AT that passes through the center of the semicircle, and any chord that passes through the center of the semicircle must be the diameter of the semicircle. So here AT that passes through the center of the semicircle must be the diameter of the semicircle. So AT is the diameter of the semicircle. I will explain again. Chord AT passes through the center of the semicircle, therefore chord AT is the diameter of the semicircle. Okay? Any chord that passes through the center of the semicircle must be the diameter of the semicircle. In the next step, we'll join points T and D together by a straight line. We join points A and D together by a straight line. So here we created peripheral angle ADT. Peripheral angle ADT rests on AT, that is the diameter of the circle. And we have here rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of the circle or semicircle must be equal to 90 degrees. Here we have peripheral angle A and B that rest on A and B, that is the diameter of the circle, therefore peripheral angle A and B equals to 90 degrees. We can implement rule number 5 in our drawing, because in our drawing we have peripheral angle ADM that rests on AT, that is the diameter of the semicircle, therefore according to rule number 5, peripheral angle ADM equals to 90 degrees. This peripheral angle ADM equals to 90 degrees according to rule number 5. Okay, so in the next step we will define angle ATD as alpha. We define angle DAT as beta. We'll focus on the right triangle, triangle ADT. On the right triangle, triangle ADT, this angle equals to 90 degrees. Therefore, the sum of the other two angles must be also equal to 90 degrees because the sum of the angles in any triangle is 180 degrees. So if this angle equals to 90 degrees, the sum of the other two angles, that is to say alpha plus beta, must be equal to 90 degrees also. So here alpha plus beta equals to 90 degrees. Here we subtract alpha from this equation and we get that beta equals to 90 degrees minus alpha. We subtract alpha from this equation and we subtract beta from this equation and we get that alpha equals to 90 degrees minus beta. Okay, in the next step we will focus on the right green triangle, triangle ADC. In the right green triangle, triangle ADC, this angle equals to 90 degrees. This angle equals to beta, therefore this angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in any triangle. So this angle must be equal to 90 degrees minus beta. But we have already found out that 90 degrees minus beta equals to alpha. So we can write here that this angle equals to alpha. Likewise, we focus on the right triangle, triangle CDT. On the right triangle, triangle CDT, this angle equals to 90 degrees. This angle equals to alpha. Therefore, this angle must be equal to 90 degrees minus alpha. But we have already found out that 90 degrees minus alpha equals to beta. So we can write here that this angle equals to beta. In the next step, we'll prove that the right green triangle, triangle ACD, this right triangle, is similar to the right green triangle, triangle CDT. Okay, so I write it down. We'll prove that the right green triangle, triangle ACD, is similar to the right green triangle, triangle CDT. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. So angle ADC, this angle, is equal to this angle, that is actually angle CTD. They are both equal to alpha, therefore they are equal to each other. In addition, those two angles, they are both equal to beta, therefore they are equal to each other. So this angle is angle CAD. Angle CAD equals to angle CDT. They are both equal to beta, therefore they are equal to each other. And finally, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So angle ACD is equal to this angle, that is angle TCD. They are both equal to 90 degrees, therefore they are equal to each other. So we actually found out that those two triangles are similar to each other according to angle similarity rule. So I write it down, triangle ACD is similar to triangle CDT according to angle similarity rule. And for the fact that the two right triangles are similar to each other, we derive that the following relationship exists between the sides. we derive that AC over CD equals to CD over CT. If it again, we derive that AC over CD equals to CD over CT. AC equals to capital R minus 2R, CD equals to 8, and CT equals to capital R plus 2R. So in conclusion, we found out that capital R minus 2R over 8 equals to 8 over capital R plus 2R. Here we post multiply this equation number 1, and we get that according to equation number 1, 8 times 8 is 64. That is equal to capital R plus 2R times capital R minus 2R. So according to this equation number 1, 64 equals to capital R plus 2R times capital R minus 2R. We have already found out that this expression equals to capital R square minus 4R square. Okay, according to equation number 1, 64 equals to capital R square minus 4R square. What is the area of the green shape? The area of the green shape, it is equal to the area of the quarter circle minus the area of the small circle. I'll repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle, that is pi R square. Here we took pi over 4 as a common factor out of those two expressions. Inside the brackets we left only with capital R square minus 4R square. But we already found out that capital R square minus 4R square equals to 64. Therefore, we can substitute capital R square minus 4R square by 64 in this equation, and you get that this expression in total equals to pi over 4 times 64. 64 over 4 is 16, so this expression equals to, in total, to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, so in terms of numbers, it is equal to 50.265 square units. So we finish the third method, and with the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. In the drawing, we have square ABCD. Inside square ABCD, we have the circle. We know that angle CBT equals to 30 degrees. Line segment PD equals to 5 units, and our mission is to find out the area of this circle. We define the center of this circle as O. We have the radius OP that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees. We have the radius OQ that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees. We know that all the angles inside square ABCD are right angles, so all those 4 angles are right angles. And especially this angle, it is a right angle. So inside quadrilateral AQPO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral AQPO, we have 4 right angles. Therefore, quadrilateral AQPO is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AQ equals to PO. But we already found out that PO equals to R. And from this equation, AQ equals to PO equals to R, we derive that AQ is also equals to R. Here, AQ equals to R. Likewise, according to the sum of the opposite sides of a rectangle are equal to each other, we get that AP equals to QO. But we have already found out that QO equals to R. And from this equation, AP equals to QO equals to R, we derive that AP is also equals to R. Here, AP is also equals to R, so we found out that quadrilateral AQPO is not a rectangle but a square. Why? Because all of its sides are equal to each other, they are equal to R. And we know that in square ABCD, all the sides are equal to each other. That is to say, side AD equals to side AB. In square ABCD, side AD equals to side AB. What is the length of side AD? Side AD equals to R plus 5. What is the length of side AB? Side AB equals to R plus QB. So, in conclusion, we found out that R plus 5 equals to R plus QB. We subtracted R from this equation and we found out that QB equals to 5. Here, QB equals to 5 units. Then, I presented to you rule number 2 and we implemented rule number 2 in our drawing. According to rule number 2, the lengths of 2 tangents from a common extreme point to a circle are equal. We have the common extreme point P. From the common extreme point P, we have 2 tangents to this circle. We have tangent PA and tangent PB. According to this rule number 2, PA equals to PB. We can implement rule number 2 in our drawing, because in our drawing we have the common extreme point B. From the common extreme point B, we have 2 tangents to the circle, tangent PQ and tangent PS. And according to rule number 2, they are equal to each other. BQ equals to BS according to rule number 2. But we have already found out that BQ equals to 5 units, and from this equation 5 equals to BQ equals to BS, we derive that BS is also equals to 5 units. Here, BS equals to 5 units. Then we joined points Q and S together by a straight line. By joining points Q and S, we created the triangle QSB. What is the size of this angle? The size of this angle equals to the size of angle ABC minus the size of angle TBC. Angle ABC equals to 90 degrees, angle TBC equals to 30 degrees, therefore this angle equals to 90 degrees minus 30 degrees, that is 60 degrees. In triangle QBS, those 2 sides are both equal to 5 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So in triangle QBS, in front of those 2 equal sides, we have those 2 angles. So those 2 angles that are located in front of equal sides must be equal to each other. So if this angle is alpha, this angle must be also equal to alpha. What is the sum of those 2 angles? The sum of those 2 angles must be equal to 180 degrees minus 60 degrees. 180 degrees minus 60 degrees is 120 degrees. Therefore, 120 degrees is the sum of the two angles, that is to say alpha plus alpha equals to 120 degrees. Alpha plus alpha is 2 alpha, that is equal to 120 degrees. We divided this equation by 2 and found out that angle alpha equals to 60 degrees. So this is angle alpha that is equal to 60 degrees, and this is angle alpha that is also equal to 60 degrees. So inside triangle QSB, all the angles are equal to 60 degrees, therefore triangle QSB is an equilateral triangle. And we know that in equilateral triangle, all the sides are equal to each other. That is to say, side AB equals to side QB, they are both equal to 5 units, therefore the missing side, side QS, must be also equal to 5 units. Here QS equals to 5 units. Then we joined points O and S together by a straight line. Point O is the center of the circle, point S is the point of the circle itself, therefore OS is the radius of the circle that is equal to R. We have the radius OS that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. Then I copied quadrilateral QBOS in a new page and we analyzed quadrilateral QBOS. This is quadrilateral QBOS that I copied from the original drawing. Triangle Q in quadrilateral QBOS, those two angles are both right angles. This angle equals to 60 degrees, and this is the missing angle. Angle QOS is the missing angle. So what is the size of the missing angle, angle QOS? It must be equal to the sum of the angles in any quadrilateral that is 360 degrees minus the sum of the three other angles. The sum of three other angles is 90 degrees plus 90 degrees plus 60 degrees. That is 240 degrees. So, in conclusion, we found out that the size of the missing angle equals to 360 degrees minus 240 degrees, that is 120 degrees. So this angle equals to 120 degrees in its size. Here, angle QOS equals to 120 degrees. Then, I presented to you the law of cosines, and we implemented the law of cosines in the green triangle, triangle QOS. What is the law of cosines? The law of cosines is true in any triangle. So if you have triangle ABC that could be any triangle, the length of side AB is A units, the length of side AC is B units, and side BC equals to C units in its length, and the angle between side AB and side AC is theta. Then according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Again, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. We implemented the law of cosines in this triangle, triangle QOS. According to the law of cosines, 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. Again, 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. 5 squared is 25, R squared plus R squared is 2R squared, minus 2 times R is minus 2R squared, times cosine 120 degrees. Cosine 120 degrees is minus 1/2. So we substituted cosine 120 degrees by minus 1/2. So we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. Minus times minus is plus, so this expression in total equals to plus R squared. So we found out that 25 equals to 2R squared plus R squared, that is 3R squared. So 25 equals to 3R squared. We divided this equation by 3 and found out that R squared equals to 25 over 3. So we found out that R squared equals to 25 over 3, and the area of our circle is pi R squared. But we already found out that R squared equals to 25 over 3, so we can substitute R squared in this equation by 25 over 3. We did it, we got that the area of our circle equals to either 25 pi over 3 square units, so in terms of numbers, it is equal to 26.18 square units. We finished with the first question, then I presented to you the second question, and we solved the second question in 3 different methods. quarter circle. Inside the quarter circle we have a small circle. Line segment CD equals to 8 units, angle ACD equals to 90 degrees, and our mission is to find out the value of the green area. So first of all, we defined the center of the small circle as J. Here we have the radius JE that is drawn to the point of tendency, therefore this angle equals to 90 degrees. We have the radius JF that is drawn to the point of tendency, therefore this angle equals to 90 degrees. And because of the fact that AOB is a quarter circle, point O must be the center of the quarter circle. This angle AOB must be equal to 90 degrees, and AO must be the radius of the quarter circle that we defined as capital R. Then from the center of the small circle, that is to say from point J, we go perpendicular on CO. Again, from point J, we go perpendicular on CO. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the starting point of the perpendicular from point J in CO as T. So inside quadrilateral CETJ, in the upper quadrilateral, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Inside the lower quadrilateral TJOF, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So we found out that this angle EJF equals to 90 degrees plus 90 degrees, that is 180 degrees. So angle EJF equals to 180 degrees, therefore angle EJF is a straight line. If angle EJF is a straight line, then line segment EJF is a straight line, and therefore line segment EF is also a straight line. And if EF is a straight line, it means that quadrilateral CEOF is a rectangle. Why? Because quadrilateral CEOF has 4 right angles, therefore it is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, CO equals to EF. CO equals to EF, but we have only found out that EF equals to R plus R, that is 2R. And from this equation, CO equals to EF equals to 2R, we derive that CO is also equals to 2R. Then implemented the Pythagoras theorem. Actually, we joined points O and D together by a straight line. Point O is the center of the quarter circle, point D is the point on the quarter circle itself, therefore OD is the radius of the quarter circle that is equal to capital R. Then we implemented the Pythagoras theorem on the right green triangle, triangle COD. According to the Pythagoras theorem in the right green triangle, triangle COD, OD square equals to CO square plus CD square. I repeat again, according to the Pythagoras theorem in the right green triangle, triangle COD, OD square equals to CO square plus CD square. OD equals to capital R, therefore OD square is capital R square, plus CO square. CO equals to 2R, therefore CO square equals to 2R square, that is 4R square plus CD square. CD equals to 8 units according to what is given in the question, therefore CD square is 8 squared, that is 64. So in conclusion, we found out that according to equation number 1, capital R square equals to 4R square plus 64. We subtracted 4R square from this equation, we found out that capital R square minus 4R square equals to 64. But what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. I repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. Okay. The area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle, that is pi R square. We took pi over 4 as a common factor out of those two expressions. So what is left from pi times capital R square over 4 after we took from it pi over 4 as a common factor? What is left? It is actually capital R square. And what is left from minus pi R square after we took from it pi over 4 as a common factor? What is left? It is actually minus 4R square. Why? Because minus 4R square times pi over 4 equals to minus 4R square. But we have already found out that this expression capital R square minus 4R square equals to 64. Therefore, we can substitute this expression by 64. We did it, and we got that this expression in total equals to pi over 4 times 64. 64 over 4 is 16. So in total, we found out that the area of the green shape equals to either 16 pi square units, so in terms of numbers, it is equal to 50.265 square units. So we finished with the first method, then I presented to you the second method. We already found out that CO equals to 2R, AO equals to capital R, it is the radius of the quarter circle. We already found out that this angle equals to 90 degrees, this angle equals to 90 degrees. And here we completed the quarter circle to a circle. Then we extended the radius AO by a straight line until it touches the circle at point T. Point O is the center of the big circle. Point T is the point of the big circle itself, therefore OT is the radius of the big circle that is equal to capital R. Then we extended the straight line DC by a straight line until it touches the circle at point M. When you extend the straight line by a straight line, the result is a straight line. So MD is a straight line. If we focus on the lower side of the straight line MD at point C, here the sum of the angles must be equal to 180 degrees according to rule number 3. So which angles we have at the lower side of MD at point C? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. So therefore, the missing angle must be also equal to 90 degrees. In order to complete the sum of the angles in the lower side of MD at point C to 180 degrees, this angle must be also equal to 90 degrees. So we have here two right angles, and we actually proved that those two right angles can go into each other. Why they can go into each other? First of all, they have a common side. CO is a common side that belongs to both triangles, so CO equals to itself. In addition, we have DO that is equal to OM. They are the area of the big circle, therefore they are equal to each other. So we found out that in these two right triangles, CO equals to CO is a common side, MO equals to OD, they are both the area of the big circle, therefore they are equal to each other. By proving that the hypotenuse and one perpendicular on those two right triangles can go in, we actually proved that those two right triangles can go into each other. Why? Because the third side must also can go in. I'll explain what I mean. Here we have two right triangles that can go into each other by their hypotenuses and one perpendicular. In both right triangles, the hypotenuse AC equals here to the hypotenuse DF, they are both equal to 5 units, and the perpendicular AB equals to the perpendicular DE, they are both equal to 4 units, therefore they are equal to each other. Therefore, the third side that is BC must also can go in. Why? Because the value of the third side, according to the Pythagoras theorem, here BC equals to the square root of 5 square minus 4 square. The square root of 5 square minus 4 square is 3. So we actually found out that if we have in two right triangles hypotenuse and one perpendicular that can go in, then the third side must also can go in. Okay, so therefore here we have also the hypotenuse and one perpendicular that can go in, therefore the third side must also can go in, and therefore those two right triangles can go into each other according to side rule. Okay, so we found out that triangle MOC can go into triangle OCD according to side rule. From the fact that they can go into each other, we derive that DC equals to CM according to the rule that corresponding sides that can go into triangles are equal to each other. Those two right triangles can go into each other, therefore the corresponding sides, that is to say CD and MC, must be also equal to each other. But it is given as the equation that DC equals to 8 units. So here, and for this equation, 8 equals to DC equals to CM, we derive that CM is also equals to 8 units. Here, CM is also equals to 8 units. Then I presented to you rule number 11, and we implemented rule number 11 in our drawing. According to rule number 11, if chord AB intersects with chord CD at point O, then according to rule number 11, AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 11 in our drawing. Why? Because in our drawing we have chord AT that intersects with chord MD at point C. And then again, chord AT intersects with chord MD at point C. Therefore, here I repeat again, we have in our drawing we have chord AT that intersects with chord MD at point C. Therefore, according to rule number 11, we get that MC times CD equals to AC times CT. Again, MC times CD equals to AC times CT. Repeat again, MC times CD equals to AC times CT according to rule number 11. MC equals to 8, CD equals to 8, so MC times CD is 8 times 8, it's a 64. AC equals to capital R minus 2R, CT equals to capital R plus 2R. So if I know that 64 equals to capital R plus 2R times capital R minus 2R. What is the value of this expression? According to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. In our specific expression, A equals to capital R and B equals to 2R. Therefore, A squared minus B squared equals to A is capital R, so A squared is capital R squared minus B squared. B is 2R, so minus B squared is minus 2R squared. So this expression in total equals to capital R squared minus 2R squared. So, and capital R squared minus 2R squared equals to capital R squared, and minus 2R squared is minus 4R squared. So in conclusion, we found out that 64 equals to capital R squared minus 4R squared. Okay. But what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. I repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle is pi times capital R square over 4 minus the area of the small circle, that is pi R square. Then we took pi over 4 as a common factor out of those two expressions, so inside the brackets we left only with capital R square minus 4R square. But we already found out that capital R square minus 4R square equals to 64, therefore we can substitute capital R square minus 4R square in this equation by 64. We did it, and we got that this expression in total equals to pi over 4 times 64. 64 over 4 is 16. So in conclusion, we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the second method. Then I presented to you how to find out the area of this green shape according to the third method. We already found out that CO equals to 2R, AO equals to capital R, this angle equals to 90 degrees, this angle equals to 90 degrees, and we already found out in the second method that AC equals to capital R minus 2R. Okay? Then we completed the quarter circle to a semicircle, and we extended the radius AO by a straight line until it touches the circle at point T. Point O is the center of the semicircle. Point T is the point of the semicircle itself, therefore OT is the radius of the semicircle that is equal to capital R. When you extend a straight line by a straight line, the result is a straight line. So the radius AO is a straight line, we extended it by a straight line, therefore the result, that is AT, must be also a straight line. AT is a straight line, so you can see AT as a chord. AT is a straight line, therefore we can see AT as a chord. So we have here chord AT that passes through the center of this circle, and any chord that passes through the center of the semicircle must be the diameter of the semicircle. Therefore, chord AD that passes through point O, that is the center of the semicircle, must be the diameter of the semicircle. So AT is the diameter of the semicircle. Then we join points A and D together by a straight line, we join points T and T by a straight line, and created peripheral angle ADT. Peripheral angle ADT rests on AT, that is the diameter of the circle. And we have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of the circle or semicircle must be equal to 90 degrees. We have peripheral angle A and B that rests on AB, that is the diameter of the circle. Therefore, peripheral angle A and B equals to 90 degrees according to this rule number 5. We can implement rule number 5 in our domain, because in our domain we have peripheral angle ADT that rests on AT, that is the diameter of the semicircle. Therefore, peripheral angle ADT, this angle, equals to 90 degrees. Then we focus on the right triangle, triangle ADT. The right triangle, triangle ADT, this angle equals to 90 degrees. Okay? And then we define this angle as alpha and this angle as beta. So if this angle equals to 90 degrees in the right triangle ADT, the other two angles must be also equal to 90 degrees. In order to complete the sum of the angles in this triangle to 180 degrees, the other two angles must be also equal to 90 degrees. That is to say, alpha plus beta equals to 90 degrees. We subtracted alpha from this equation and found out that beta equals to 90 degrees minus alpha. Then we subtracted beta from this equation and found out that alpha equals to 90 degrees minus beta. So then we focus on the right green triangle, triangle ACD. This angle equals to beta. This angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees, that is the sum of the angles in any triangle. So this angle must be equal to 90 degrees minus beta, but we already found out that 90 degrees minus beta equals to alpha. So we can substitute 90 degrees minus beta here by alpha. Then, likewise, in the right triangle CDT, this angle equals to 90 degrees. This angle equals to alpha, therefore this angle must be equal to 90 degrees minus alpha. But we already found out that 90 degrees minus alpha equals to beta, so we can substitute 90 degrees minus alpha here by beta. Then we proved that the right green triangle, triangle ACD, is similar to the right green triangle, triangle CDT. So, why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to beta, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So we proved that those two right angles are similar to each other according to angle similarity rule. And from the fact that they are similar to each other, we conclude that the following relationship exists between their sides. We conclude that AC over CD equals to CD over CT. Again, AC over CD equals to CD over CT. AC is capital R minus 2R, CD is 8, and CT is capital R plus 2R. Here we cross multiply this equation and found out that 8 times 8 is 64. That is equal to capital R plus 2R times capital R minus 2R. But we already found out that capital R plus 2R times capital R minus 2R equals to capital R square minus 4R square. So in conclusion, we found out that according to equation number 1, 64 equals to capital R square minus 4R square. Okay? But what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. I repeat again. the area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle is pi times capital R square over 4 minus the area of the small circle. The area of the small circle is pi R square over 4. We took pi over 4 as a common factor of those two expressions, so inside the brackets we left only with capital R square minus 4R square. But we have only found out that capital R square minus 4R square equals to 64. Therefore, we can substitute capital R square minus 4R square here by 64. We did it, and we got that this expression in total equals to pi over 4 times 64. 64 over 4 is 16. So in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. So in all three methods, we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. Okay? Thank you very much.